In this lecture, we will look at the ways that the laws of probability are used in the study of the transmission of Mendelian genetics. We're going to do a very brief overview of the laws of probability. We will look at the ways that these laws can be applied, and we'll sort of discuss the basics. There will be many examples we'll have an opportunity to work together in class. So let's review the basic laws of probability. When we mention the word probability, we have in mind, of course, the likelihood of the occurrence of a particular event based on the circumstances in the problem that we're interested in. Probability is widely used in genetics, primarily in our circumstances today, to predict the outcome of a particular genetic cross. It could be the likelihood of a certain genotype, it could be the likelihood of a certain phenotype. We're going to begin with a review of two rules, the addition rule and the multiplication rule. What the addition rule states is if there are multiple ways to meet a certain criteria, you add the probability of all of the possible ways or paths to meet that criteria. So, for example, if we were to say, what is the probability of rolling a six-sided die and getting a third? That would be, a 3. That would be 1/6. If we said, what is the probability of rolling a six-sided die and getting a 4? That would also be 1/6. So in question A, there's only one possible outcome that meets my criteria. What is the probability of rolling a 3? There are no other numbers that meet that criteria. And in my second question, what is the probability of rolling a 4? There is only one way to meet my criteria. If I don't roll a 4, I have not met my criteria. But if I ask the question, what is the probability of getting either a 3 or a 4, I have now provided multiple ways to meet my criteria, and in this case there's two, a 3 or a 4. And I hope that it's intuitive to you that the more opportunities or pathways you create to meet your criteria, the more likely it is that you will meet it. And therefore what we need to do is we need to add these probabilities together, and then of course we get 2/6, which we can then simplify to 1/3. The key word that we're looking for here is or. When we see or, we're adding multiple pathways to meet our criteria, and therefore we want to apply the addition rule. So the addition rule is used to calculate the probability of two independent events occurring separately. So there's two different ways to meet our criteria. They're not linked in any way. You could get one pathway or another pathway. They're probabilistically independent, and they all meet the criteria. You need to add those probabilities together. So here's the different version of the same problem. What is the probability of rolling a 1 on a six-sided die? That's 1/6. The probability of rolling a 6 is also 1/6. And if I say or, I must add those together to get 2/6, which is 1/3. Let's say Johnny has a six-sided die and a 10-sided die. What is the probability of rolling a 4 on the six-sided die and the 8, or an 8 on the 10-sided die? So the probability of rolling a 4 is 1/6. The probability of rolling an 8 is 1/10. So since I have used the word or, I am going to meet my criteria whether I roll a 4 on the six-sided die or I roll an 8 on the 10-sided die. So then what I need to do is I need to add these two probabilities together. So if we remember our basic rules for how we add fractions, we need to find the least common denominator so that we can add them together. So the least common denominator in this case is 30. So we would multiply 6 times 5 to get 30. 5/30ths is the same as 1/6. And then we multiply times 3, and we would get 8/30ths, which we would then simplify into 4/15ths. Now to turn to the multiplication rule. The multiplication rule describes how you address scenarios in which, rather than increasing the pathways to meet your criteria, you are increasing the specificity of what you're looking for. So you're actually cutting down on the ways to meet your criteria. So as an example of this, let's take this scenario. We're asked, what is the probability that we roll a 6 on a 6-sided die? And the answer, of course, is 1/6. And we might ask then, well, what is the probability of rolling a 6 and then on a second roll, rolling a 6? Well, this is a more specific scenario, because on the first roll, I have to get exactly a 6, and on the second roll, if I get anything else, I failed. I must also get a 6 again. So I've been much more specific than in my previous example, and so what you do is you multiply the probabilities of each event occurring together, and you get 1/36th, which is much smaller than the previous example. So in the previous example, what we asked was, what was the probability of getting a 3 or a 4? And because we are creating two possible ways to meet our criteria, what we said was we're going to add these probabilities together and get 1/3. But if we said, what is the probability of getting a 3 on the first roll and then on the second roll getting a 4? Well, now we're talking about something completely different. We're not creating extra pathways to meet our criteria. We're actually decreasing the ways to meet our criteria. And so instead of adding them together, we would need to multiply them together to end up with a probability that is much lower. So what I want you to kind of intuitively wrap your brain around is that when we are being more specific about the offspring that we are discussing in our genetic cross, we're going to use the multiplication rule, and we should expect the probability to decrease. But when we are creating multiple avenues to meet our criteria, then we are increasing the likelihood, and we should use the addition rule. So our key word for the multiplication rule is and. When we see and, when we're linking events together, we're using the multiplication rule. So the multiplication rule is used to calculate the probability of two independent events occurring together. So let's say we're using a 6-sided die. What is the probability of rolling it 3 times and in each roll getting a 6? Well, the probability of any individual 6th is 1/6. Probability of 6 is 1/6. So therefore, the probability of getting a 6 and then a 6 and then a 6 would be 1/6 times 1/6 times 1/6. And therefore, the answer is 216. Much, much lower. So that's kind of basic. Let's look at some situations that increase the complexity. One of the things that can quickly increase the complexity of the problem is something we refer to as conditional probability. And conditional probability basically states, I have more information, and that information has decreased or changed or increased the probability. So I know more now because an event has happened, some other event has occurred, and that changes the likelihood that I'm interested in. So let's take this as an example. Let's say we do a standard monohybrid cross. So we can sketch this out, standard monohybrid cross. And we can go ahead and fill it in. So that's the standard genotypic pattern of a monohybrid cross. And remember that the monohybrid cross works because of Mendel's first law, the law of segregation. Okay? So we did a monohybrid cross. Notice we've already done it. We're not talking about a future hypothetical. We're talking about an event that has occurred. The offspring of that cross, so one of the offspring has the tall phenotype. So let's say we're dealing in plants, like Mendel's pea plants. Mendel does the monohybrid cross. One of the offsprings is the dominant phenotype. That plant is sitting on his desk. He's looking at it, and he says, that obviously has the dominant phenotype. But this plant could be homozygous dominant or heterozygous dominant. And so we don't know which one it is. We just know that it's tall. And so we ask the question, what is the probability that the tall offspring's genotype is heterozygous? So that's what we're asking. What is the probability that this individual is heterozygous? Now take a minute and think about it. Now, we may be tempted to say, well, if I look at the monohybrid cross, the probability of a heterozygote is 1/2. But we would be incorrect in this case. If I had asked, if you do a monohybrid cross, what is the probability that you get a heterozygote? The answer would be 1/2. But that's not the question that's asked. The question that is asked is, this individual who is born from a monohybrid cross is tall. So if the individual is already tall, the only possible outcomes are these. And that means that this is not describing the individual. Because if the individual was homozygous recessive, they would be short. So what I have is 3 possible genotypes given the facts that I know. And of those 3, 2 out of 3 are heterozygous. And so the answer in this case is 2/3. Now that may seem counterintuitive, right? But what's really happening here is we're saying, now that we know that the individual has the dominant phenotype, that information is changing the probability, the conditions of the probability have been altered, and we have to take that into account. Another thing that we deal with when we deal with probability is how quickly these problems can get very complicated when we start talking about multiple alleles, multiple phenotypes. We have to account for every possible way that the criteria can be met. Let's go over some examples to see how complex this can be. Albinism is a recessive Mendelian disorder causing reduced pigmentation of the skin and the eyes. Okay, so it's a recessive, autosomal recessive disorder. It follows basic Mendelian rules. And we ask, what is the probability of having one child with albinism and 2 children with normal pigmentation if both of the parents are carriers? So we sketch out. Neither parent has albinism, but they're both carriers for the trait. Okay, so what I want to know is, what is the probability of having one child who is albinism and 2 children that have normal pigmentation? So the probability of having albinism is 1/4, and the probability of having normal pigmentation is 3/4. Okay, so we might be tempted to say, well, then my answer is 1/4 times 3/4 times 3/4. We might be tempted to say that. The problem is if we present the problem in this way, we have laid out the order of the children so that the oldest has albinism, the second does not have albinism, and the third does not. There are, however, multiple ways to end up with one child who has albinism and two children that do not. It could be that the first child is in fact an albino and the other two children are not. The child with albinism could be the second child or could be the third child. And you have to account for every possible pattern because every possible pattern meets the criteria. Now, if I ask the question, what is the probability that the first child will have albinism and the second child will not and the third child will not, then A would be the only one that fills my criteria. But I didn't ask that question. The parents just said, look, we plan on having 3 kids. What is the probability that we have one with albinism? And so we have to use the multiplication rule for all of these opportunities, but then we must add them together to get the real full probability. So this mechanism, we said this was 1/4, 3/4, and 3/4. That's 9/64. But it's actually much more likely than that because there are other ways to do it. And so you have to add 9/64 and 9/64 together to get an actual probability of 27/64, which is almost a half. So if you had only accounted for the first opportunity, selection A, or just selection B or selection C, you would vastly underestimate the probability of having one child with albinism out of 3 children because it's almost 50%. Now let's look at another example. What is the probability of having 2 children with albinism and 3 children with normal pigmentation? Well, now I think you're beginning to see how complicated this scenario could be if you need to sit down and think about all of the different ways that it could happen. And in a high stress situation, for example, while you're taking an exam, it's very likely that you will not account for all of the multiple ways in which you can meet the criteria. And if you base your strategy on answering this question by being able to write out option A, option B, option C, it's highly likely that you'll forget one. I know that I would. So there has to be a better way of dealing with this. Well, there is another way of dealing with it. One way is to use the binomial expansion. And you can do this if this is something that you're interested in. You could say P represents the probability of scenario 1, in this case albinism. Q represents the probability of a child without albinism. I'm dealing with 5 children, so my binomial would be P plus Q raised to the 5th, and then you have to expand that out to solve it. And if it's been a while since you've looked at binomial expansion, this would be your formula here on the bottom. Now, that's not super helpful to me. That may even be worse than just trying to sit down and think about what are all the different scenarios. You can do this. This works perfectly fine, but there is another option. The other option is to use this particular formula. I would recommend that you memorize this formula. The probability is equal to n factorial divided by s factorial t factorial multiplied by p raised to the s, q raised to the t. I would encourage you to memorize this formula. Now, what do all these letters represent? N represents the total number of children. P is the probability of the first event. Q is the probability of the second event. S is the number of P events. and T is the number of Q events. So it doesn't matter. You could define P as the probability of albinism. You could define P as the probability of normal pigmentation. What's critical is that P must always go with S and Q must always go with T. You can't mix those up. If you mix those up, you're going to be in trouble. Now let's remember what a factorial is. A factorial is when, that's what that exclamation point symbol means. It means you take the number and you multiply it in a series by every number down to 1. So 3 factorial would equal 3 times 2 times 1. 4 factorial would equal 4 times 3 times 2 times 1. Okay, so that's what that little factorial exclamation symbol means. So if we write this out, the total number of children is 5. The number of, in this case we said P was going to be albinism. Q was going to be non-albinism. Okay, my N value, my total number of children was 5. My S was 2. My T, my number of children without albinism, was 3. So S factorial is 2. T factorial is 3. And I multiply the probability of albinism in our previous example is 1/4 raised to 2 multiplied by 3/4 raised to the 3rd. If you calculate that out, your answer is about 1/4, 0.26. So the probability of having 5 children, 2 with albinism, is relatively high. And that's because there are multiple ways in which you can meet that criteria. Now we're going to work example problems like this in class, and I'll bring in some calculators and I'll remind you how to do the factorial and raise to the power and all of that. But I hope that this overview of the laws of probability has been a good refresher for you. Think about how these problems work, go back and look over the examples, and we'll get together in class and we'll work several examples together.